Hi, everybody. There's a section of chapter 5, which I inadvertently never posted the video. This is the video. This is the video, and it's just part of 5.5, and it's this thing called cross products. And a cross product is something that if you take Calc 3, which some of you may have already taken Calc 3, you'll learn about this thing called cross products, and it's a very simple thing. I'm actually going to have one question on the test about cross products, and I'll even tell you exactly what the question is. I won't tell you the numbers, but I'll tell you the point of the question. But let me explain what cross products are. So first of all, a cross product is only defined on vectors in R3. There's no such thing as a cross product in R2 or R5 or anything like that. It's only R3. That's number one. Secondly, a dot product of two vectors is a number, a scalar. You multiply the components in that dot product way, and you get some scalar number. A cross product of two vectors is another vector. Now, the definition of cross product here, which is like very hard to read, is a much easier way to say it, and it's like this: U cross V is equal to, now on top you have I, J, and K. Now I is the vector. I is the vector 1, 0, 0, J is the vector 0, 1, 0, and K is the vector 0, 0, 1. So U cross V is the determinant which has on top I, J, K. The second row is the components of the U vector, U1, U2, U3, and third row is the components of the V vector, V1, V2, V3. So now when you multiply this all out, the way we learned how to do determinants, you wind up getting this matrix, this 2 by 2 matrix times the I times the vector I. We're going to go across the top row, and you get this matrix, this determinant times the vector J, and that determinant the vector K. When you multiply out these determinants, you get this expression down here, which is the exact same as what it says in here. So whatever way you want to say it, that's the determinant. Now, notice right away we could see that if we do V cross U, V cross U is going to be the same as U cross V. The only difference is the V's are going to be the middle row and the U's are going to be the bottom row, which means, as you all know, as we learned already, V cross U is going to be the negative of U cross V, because we know that when you switch two rows in a matrix, it makes the determinant negative. So that's right. You see, we already very quickly see a property of determinants and cross products. So let's and it has a lot of words. You may have seen it in physics, cross products and vectors and so forth. But let's just look at an example. We're just doing a basic cross product. So here's a vector. U is 1 minus 2j plus k. V is 3i plus j minus 2k. We normally sometimes we'll write this vector that U is 1 comma negative 2 comma 1, and V is 3 comma 1 comma negative 2. That's another way to write the same vector. Anyway, U cross V, V cross U, and V cross V. Well, U cross V is this sucker right here, which if you multiply it out, comes out to 357, 3i plus 5j plus 7k. V cross U is that vector, is this determinant over here, which if you multiply it out, comes out to negative 3i minus 5j minus 7k. And again, that makes sense because the difference between this determinant and that determinant is that I switched two rows, and that makes the determinant negative. Now let's look at V cross V. V cross V is going to be 0. V cross V is going to be 0, and that is not a coincidence. And especially since we know, because why? Because V cross V, why is it obvious that it's going to be 0? Well, you have the second row and the third row are the exact same thing. And we know that we've learned already that if you have a matrix where two rows are identical, then the determinant will be 0. So again, V cross V equals 0, not shocking at all. And here's some algebraic properties. U cross U equals 0, like we just explained. U cross V equals negative V cross U, and so on and so forth. Okay, well, I'm not going to go into this in great detail. I'm just going to say that when you take a cross product of two vectors in R3, you get a third vector which is orthogonal to both of the original two vectors. When you take a, in fact, I'm going to even type that out for you. When you take a cross product